We've already discussed the exponential Fourier series.
Yeah. Given that sinusoids make up continuous time complex exponentials, can't we have a Fourier series using sines and cosines?
To answer this question, we'll ask a few more questions.
Huh?
For example, are two sine waves orthogonal to each other?
Hmm.
What about cosines?
Uh,
And what about sine and cosine?
okay, wait. Why are we even talking about orthogonality?
Remember, it was the orthogonality of harmonically related complex exponentials that led us to the exponential Fourier series.
Oh, so if harmonically related sinusoids are orthogonal to each other, we'd get to the trigonometric Fourier series?
Yep.
Oh, okay. Then what does it even mean for two sinusoids to be orthogonal in the first place?
Good question. Let's review. To see how the vector y contributes to constructing the vector x, we project x onto the vector y. Now this projection turns out to be 0 when x is perpendicular or orthogonal to y.
Yeah.
Mathematically, this projection is computed using the inner product, or in this case, the dot product of the two vectors.
So two vectors are orthogonal if their inner product turns out to be 0?
Yep. This means that one vector does not contribute to constructing the other vector. Only the vector 0 is common between the two. This holds good for complex vectors as well, and in general for vectors lying in an n-dimensional space. Interestingly, this idea of orthogonality can also be extended to continuous time signals. Since x of t and y of t are defined over a continuum of values of time, they can be thought of as infinite dimensional vectors. So we rewrite the summation as integration in this definition of inner product. So two signals are orthogonal to each other if this integral turns out to be 0. So in these cases, we need to check if the integrals turn out to be 0 or not.
Interesting.
Yeah, but before we evaluate these integrals, let's understand what it visually means to integrate continuous time sinusoidal signals over one time period t.
Okay.
Yeah, so integration can be interpreted as the area under the curve between the limits of integration. So in this case, the positive area above cancels the negative area below, giving us 0.
Hey, what if there's a phase shift?
It doesn't matter, the integral is still 0 over the time period.
And what if there is a change in the amplitude?
What do you think?
The areas still cancel each other out.
Exactly.
Oh, so this integral is always 0.
Not always.
Huh? But we just saw.
What if the frequency changes?
Oh.
When the frequency reduces to 0, we get this as the answer.
Oh, yeah.
Of course, if there is no effective phase shift in the sine wave and the frequency reduces to 0, we get 0.
Yeah.
We have something similar for the cosine. When frequency reduces to 0, we get this as the answer.
Yeah.
Okay, without concerning ourselves with the amplitude or the phase, we have these expressions, okay? With this idea, let's first find out if two sine waves are orthogonal to each other. We'll consider the fundamental case where both the sine waves are periodic with time t. This in turn means that the two sine waves are
harmonically related.
Exactly. Now, when we plot these two harmonically related sine waves and their product, we see that
the areas cancel each other out. Nice. This proves that sine waves are orthogonal to each other.
Not really. A single example is not good enough to prove a statement.
Oh.
But a single counterexample is enough to disprove a statement.
Makes sense.
In this case, it's not obvious that the positive and negative areas even cancel each other out.
So we need to check that this area cancels out for all possible m and n? That's hard.
That's where math comes in. You must have come across this trigonometric product to sum formula in your high school.
Yeah, I always wondered where we'd ever use them.
Well, right here to understand orthogonality in sinusoids.
And where would we use this?
You'll see. Anyway, let's plug this equation into our integral. Now when n and m are distinct, the integral becomes 0.
Oh, so harmonically related sine waves are orthogonal to each other. What if m equals n?
It's like projecting a vector onto itself.
Oh, so the projection equals the length of the vector.
Exactly. In the case of a sine wave, its length turns out to be this area. So this is what we have for the sine wave. Now using the trigonometric product to sum formula for cosine, we get this.
So harmonically related cosines are also orthogonal to each other.
Yeah.
Okay, interesting. But what's the point of knowing all this stuff?
We discussed the idea of basis vectors in an earlier episode.
Yeah, basis helps us construct every point in the space they lie in. Okay, hang on. Where exactly do these sinusoids lie?
Good question. We see that a finite magnitude sinusoid, considered over its fundamental period t, is a square integrable function. I encourage you to check for yourself that harmonically related sinusoids are also square integrable over t. Now all possible square integrable functions with a duration of t seconds lie in an infinite dimensional space denoted by L2.
Yeah, we have seen this in an earlier episode.
Yep. So harmonically related sinusoids lie in this space.
Wait a minute. Now we have two new sets of bases for L2.
What do you mean?
We already saw that harmonically related complex exponentials form one set of bases for L2. Now all the harmonically related sine waves form another set of bases and the cosines form yet another.
No.
What? Why?
Just because a bunch of vectors is orthogonal doesn't make it an orthogonal basis.
Oh.
Do you think it is possible to construct a cosine wave by adding any number of harmonically related sine waves?
Oh yeah, that doesn't seem to be possible. There's no way to get the value 1 when all the sine waves begin and end at 0.
Exactly. A good counterexample to disprove your own statement.
Oh yeah.
In fact, we see that harmonically related sines and cosines are orthogonal to each other.
Oh.
It turns out that in order to construct every function in L2, we need sines and cosines. Together, they form a basis for L2, making sinusoids a powerful representational tool. The use of infinitely many weighted harmonically related sinusoids to represent one period of a continuous time periodic signal that is square integrable is called the Trigonometric Fourier Series.
Interesting. Given the Euler's formula, aren't these two bases related in some way?
Yeah, great question. In the next episode, we'll try to understand the connection between the two and also get a visual feel for this equation.
Nice.
So, meet you in the next one.